Jimmy, may meeting ako ng 9. Kala ko 8:30 nag-start. Sorry.
It's okay.
Jimmy, may meeting ako ng 9.
Yeah.
Kala ko 8:30 nag-start. Sorry. Ay, bakit delay? Jimmy, may... Oh, inulit pa. Ano ba yan?
Yeah. That was the YouTube streaming and it was echoing, so I had to turn it off.
Kaya pala. Alam ko merong ibang Henry dyan eh. Pero darating daw si Joy pala, no? Sila Francis.
Ang ingay naman ni Sir Henry.
Ay, sorry po.
Si
Late nang ako eh. Sorry ah. Then may meeting ako 9, sir. So maya-maya alis ako. Kala ko nag-start na eh. Sorry.
We're already live. No, we're starting at 9. Not 8:30. Good morning, everyone. We will start now. This is the 10th workshop on computation, theory, and practice. For the first time, we are online. This is an online workshop, and this time it's just a one-day event. And we tried to squeeze in all the paper presenters into one day. And this today, it will extend up to 6:30 p.m. So this is the 10th workshop. It's an event that is organized by the Tokyo Institute of Technology, the Osaka University, the University of the Philippines-Diliman, and the De La Salle University. We are grateful for the co-chairs of the workshop, Professor Shinya Nishizaki, Professor Masa Numao, Professor Yami Suarez of De La Salle University. So to give the opening remarks for this event, may I introduce Professor Masa Numao.
Thank you very much. Good morning, Your Excellency and ladies and gentlemen. I want to extend greetings to all of you here today on behalf of all of the organizers. We shall have the 10th workshop on computation theory and practice 2020 online with great honor and pleasure. This time is the 10th memorial workshop. However, because of COVID-19, this becomes the first trial to have the workshop online. The online workshop has some merits. For example, we can attract more people all over the world. More than 100 people have already registered for this workshop. I want to extend our deep appreciation to each committee member supporting this virtual workshop. I desire that this workshop achieve tremendous success. Your attendance here in the workshop on computation theory and practice 2020 will prove to be a pleasant and meaningful one. Thank you.
Thank you, Professor Numao. So we are grateful for that we are able to still meet online even time when we are all worrying about the COVID, and this is so last year we had our conference with De La Salle University as host, and this year it is UP-Diliman's turn to host the conference. For our So some reminders for everyone: when you are the speaker, please turn on your audio. Don't forget to turn on your audio. And then you can start sharing your slides. After you speak, please turn off your slides. If you have, for attendees, if you have questions, please type in the Q&A. And for panelists, you can just ask your questions if you have questions, or you can type in the chat because the panelists do not have access to the Q&A. You can only read the Q&A, but you can type your questions in the chat box. So we'll try to also monitor the chat, and also the you can also ask questions orally and just unmute your microphone for panelists. Okay, so for this morning session, our moderator is Dr. Francis Cabarle of the University of the Philippines-Diliman. Francis.
Thank you, Sir Jim. Good morning to everyone attending the 10th workshop, WCTP. I'll turn off my video now to conserve bandwidth, at least from my end. So good morning. Thank you for the opening remarks and introduction, Professor Caro again and Professor Numao. So just some, again, additional few house rules. So the workshop will be hopefully more or less technical error free, and we will more or less maintain our schedule. So the talks will have, according to the program, if you have the copy of the program, each talk will have 25 minutes, and about 22 minutes will be dedicated to the talk, including the setup and so on, with about 3 minutes, 2 to 3 minutes for questions and answers. Although I think there will be some additional time later. There may be additional time later for other questions. So, and then you, in the last 3 minutes of your talk, you will hear a beep or an alarm to remind you that you have only about 3 minutes remaining. And then the second time the beep or the alarm goes off, it means you have to please end your talk to give way to the question and answer time, and of course to set up the next speaker. The earlier, of course, you can finish. There's no problem if you finish earlier. So the first speaker, can you please start opening your slides while I introduce you? The first paper, or the first talk for the morning session is by Professor Watanabe. The title is Developing Coordinating Distributed Applications in the Pure FRP Language. So you have 22 minutes. You can start now, please. Thank you very much.
Okay, so can you hear my voice and can you see the slide?
Yes.
Okay.
Yes, voice and slides. Okay, thank you.
Okay, so thank you. Thank you for introduction. So first of all, it's my honor to give a talk at this commemorative 10th WCTP, and I salute the efforts of the past and present organizers and the committee members. And I want to add my congratulations to you. Okay, so anyway, so today I'm going to talk about ongoing idea about developing distributed applications using a pure functional reactive language, which has been developed in my research group, mainly by my past student, Kazuhiro Shibanai, is the second author of this work. Okay. So here's the overview. So in this talk, I will present a method for describing wireless sensor adapter network using functional reactive programming language designed for distributed applications. And a wireless sensor actor network is a typical example of coordinating distributed systems. The contribution is that the method enables a uniform description of intranode computation and internode coordinations, both of which are essential in developing wireless sensor actor networks. Okay. Also, I will discuss an incremental development or incremental development scheme for wireless sensor actor networks. So, okay. So let me start from the brief explanation what is a wireless sensor and actor networks. Okay. Wireless sensor network, WSN in short, is a distributed system that consists of specially distributed sensor nodes and typically a single sync node. Okay. The sync node collects information measured by the sensor nodes to monitor the physical condition of the environment. A wireless sensor actor network, in contrast, WSAN in short, contains another type of node called actor nodes. The responsibilities of actor nodes include the controlling actuators and making local decisions and performing coordination tasks. So please note that the notion of actors here is different from that of the actor model, which is a concurrent computational model. Okay. So from the programming point of view, so WSAN brings several difficulties. Okay. The point is that we should consider two aspects, distribution and reactivity. The first thing is that WSN is a distributed system. So we need to consider coordination, which indicates a pattern of communication and synchronization. Of course, we should not forget about the communication delays and the failures. The second thing is WSAN is a reactive system. A reactive system is a computational system that repeatedly reacts inputs with uncontrollable order and timing. So embedded systems and GUIs are typical examples of reactive systems. So inputs and reactions may be continuous, and timeliness is often required. And sometimes WSN performs a feedback control with its environment. And so it is very important to note that the entire network, entire WSN, not just the individual nodes, can be considered as a reactive system. So how can we write the program for such systems? So that is the whole motivation of this work. Okay. So because I'm a programming language researcher, so I consider first language-based approaches. Okay. So the possible candidate is the notion of a coordination language. So coordination languages supports the separation of inter-node coordination and intra-node computation by providing high-level communication and synchronization mechanisms. So for example, the tuple space model, also known as the Linda model, and the actor model and stream-based communication models, and published subscript models, and so on. So the role of a coordination language is to just provide a specific coordination mechanisms and not to support a way to integrate computation and communication. Okay. So it is not satisfiable for our purpose. The macro programming languages that provide a high level of abstractions mechanism for describing WSNs, wireless sensor networks. Okay. For example, using the language named Regiment, functional macro, this is functional macro programming languages. So we can write a program of WSN as single entities, like this example. Okay. So this code shown in here calculates the average temperature of the environment. So from this code, the compiler automatically generates the code for sensor nodes and sync nodes. Okay. So unfortunately, the current macro programming language do not take up actor nodes into account or provides insufficient features. So this works aim to provide a uniform, So this work aims to provide a uniform abstraction applicable to both inter-node coordination and intra-node computations. So several questions arise. So first, so are there any appropriate mechanisms to express coordination and computation? And the second, so can the mechanism deal with the distribution? And the third, is the performance acceptable? Okay. So to tackle this approach, so our approach is to use a functional reactive programming language designed for distributed systems. Okay. So what is a functional reactive programming language? Programming, FRP in short. Okay. So this is a programming paradigm for reactive systems based on the notion of functional the functional abstraction to express time-varying values, okay, and events. So the first FRP system published in past is an interactive animation library for Haskell. The Haskell is a pure functional programming language. So the central idea is the notion of time-varying values. Okay, this one. That abstracts continuously changing data. Okay. So for example, so sensor readings or mouse position and so on are examples of time-varying values. So various languages and libraries and DSLs have been developed so far. So we also designed an functional reactive language named MFRP here. So for the resource-constrained embedded systems. See. I gave a talk several times in this workshop in the past. So here's a simple example program in MFRP. So this program controls a switch of a fan according to the readings of two environmental sensors, okay, for these sensors. So the important point is that the values of these variables changes automatically over time. So what we have to do is to describe the the change propagation between the variables as just expressions. So we don't need to write polling loops or callbacks, which are typical patterns for writing reactive application in usual programming languages. So things may be very simple. And here's a language used in this work. So distributed XFRP is a pure FRP language mainly developed by the second author, Kazuhiro Shibanai. And it is a distributed extension of XFRP. XFRP is a successor of MFRP. Okay. So they are shared, but the common language design, the syntax resembles. Okay. So in distributed XFRP, the change propagation between two time-varying values can span different physical nodes. Okay. This fact implies that the language provides the sort of uniformity required in this research. And the runtime system of this language is based on the actor model. So this, so in this context, the actor model refers to the concurrent computation model, okay, not for the actor node in sensor actor wireless sensor actor network. Sorry for the, let's say, confusion. And so time-varying values are represented by actors. Okay. The change propagation realized by asynchronous messages between actors. So we implemented a compiler that translates the XFRP code into RLAN. Okay. So, and here the slides show an example, the very simple example program written in distributed XFRP. So the syntax is common with the MFRP. And it describes, this code describes a simple collaborative board. Okay? And the inputs from the keyboard at each client, connected at each client, are shown in the display at the server. So as in MFRP, the program is written as a collection of expressions defining time-varying values. So by adding annotations, so called host specifier, so these time-varying values are actually deployed at the specified physical node. So that is all for writing distributed applications in this language. but an essential point in FRP language, especially in distributed system, is the elimination of glitches. So glitch is a phenomenon about temporal inconsistencies in the propagation among the time-varying values. So for example, if the change in A propagates through X and Y at different rates to Z. So in this case, the value of Z will be unintended. Okay. So in reality, so we want to be the value of this, so not Z, not W, so but Z. The value of this value should be true for all time. Okay. So in the distributed systems, so realizing glitch freedom is not so easy, okay, of course, because of the delays in communication are significant. So by a researcher in this area, so glitch freedom is divided into two categories. The single source glitch freedom guarantees that the changing in each input are propagated to its dependence without glitches. But other sources are not considered. So this figure shows a simple single source glitch freedom. So if A is the input, so the effect of changing in A reaches to Z without any time difference. So the value of this variable is always a true. So this is implemented in distributed XFRP. And the second one, the complete glitch freedom. It's in contrast, it takes a causal relation of all inputs into account. So in this case, we have two inputs, A and B. So the order of changes in these A and B can be observed by X and Y at the same way. Okay. So no difference in order. So in this case, if this system passes complete glitch freedom, so the value of the Z is always a true. But this is not cost effective because if A and B are deployed on different physical nodes, it is not easy to synchronize or have input from these nodes. So as I said, so distributed FRP, XFRP, basically supports the single source glitch freedom because of the cost effectiveness. Okay. So detailed algorithms for value propagation is in our previous paper. Sorry. Okay, so here so now let's see how to describe the WSAN in distributed XFRP. So this figure shows a wireless sensor actor network that monitors and controls the temperature and humidity of the air in a long corridor. This is a corridor. Okay. So the corridor is divided into several segments that are numbered sequentially like this in the segment. So each auto-numbered segment is equipped with a temperature sensor and a temperature controller. And each even-numbered segment is equipped with a humidity sensor and humidity controller. So the purpose of this wireless sensor actor network is to regulate the air environment or air conditions of the corridor by lowering the difference between the difference in discomfort index among the corridor segments. So how to do that? Okay. So this box, so small white box, indicates that time varying values. Okay. And so T1, T1 and T3 and T5 indicates a correspond to the temperature sensor, and H2 and H4 and H6 correspond to the humidity sensor. And DI with numbers is a time varying value for discomfort index. That is let's say the value calculated from humidity and temperature. That's shows some disconformity by human. Okay. And DDI, difference between two adjacent discomfort index. And then, so TC1 and HC, TC and HC correspond to the temperature control and humidity controllers. The difference, how to say, the system try to minimize the difference between adjacent temperature control or humidity controllers, okay, to regulate the air environment of this corridor. So so it is a very important thing that single source glitch freedom provided by our language.
Please continue, Professor. You have 3 minutes. Thank you.
3 minutes? Okay. So the language guarantees that no temporal inconsistency can be observed in this system. So here is the code for this example. So as you can see, that code is very straightforward implementation and very easy to understand. So to deploy the time varying values to appropriate physical nodes, physical sensor or actor nodes in the wireless sensor actor network, so we can put host specifiers, okay, on top of these declarations. So, and the uniformity in the description is realized. So here I'm going to let's say discuss about incremental development of wireless sensor actor networks. Okay, so as you can see, the distributed XRP provides a uniform way to express both intranode and internode, intranode computation and internode communication or coordinations. So in addition, this language supports an incremental development. Okay, so first we can construct a prototype of the wireless sensor actor network as a single module, as in the previous slide. So that defines the entire behavior of the systems. So at this point, so the module has no host specifiers. So after some local testing, we can gradually deploy the time varying values to actual physical node by incrementally adding the host specifier and source unifiers to the module definition. So in the point, so we can say that the language plays a role of macro-programming language for WSANs and with some uniformity in these descriptions. Okay, so let me summarize my talk. So I introduced a method for describing the behavior of wireless sensor actor networks with using distributed XRP. This is a pure FRP language designed for distributed systems. And this language provides a uniform declarative way to express the both intranode communication and internode coordination. And I also discussed some direction to incremental development. For future directions, so we have to take care of some fault tolerance and dynamically configure network and real-timeness. And formal specification and verification is important. And efficient implementation for small devices are also important. The current compiler only generates, let's say, RN code. So we need that somewhat big node that can run RN. Okay. So thank you very much. That is all.
Okay, thank you very much, Professor Watanabe. So at this point, we have about 3 minutes to accept the questions from the audience. Just a reminder, you can send your questions to Professor Watanabe via using the chat window. And I think the panel members, the authors, can directly use their microphones to speak and ask questions or send comments. So so again, thank you very much, Professor Watanabe. Professor Watanabe again is from Department of Computer Science, Tokyo Institute of Technology in Japan. At the moment, there are no questions in the question and answer box. Any questions or comments from the panelists? At the moment, we have 26 panelists and 35 attendees. So let me check for questions. Okay. Check. Okay. At the moment, there are no questions. So if you, some of you who have questions, I think during the break or at an additional, at a later time, we may have
Francis, may I inquire?
Yes,
Hello,
please.
good morning.
Good morning.
Good morning,
Hi.
Dr. Francis,
Good
and good morning, Dr. Watanabe.
Morning.
Thank you for the presentation. I just would like to know the status of its implementation for actual systems, because I can see this is important for smart spaces, for example, for IoT applications. At what stage are you into actually trying it out for actual implementations? Thank
Yeah.
you.
Actually, so our current compiler, so let's say, translates the distributed XRP code into the ARAN code. So we can install deploy our program. That's the system that can run ARAN. ARAN is the name of the programming language for based on ACTA model. So unfortunately, we haven't yet experienced about the actual very large distributed systems, only for the simulations on the single node computers. Is that the answer for you?
Yes, thank you very much. We look forward to more simulations in the coming years for WCTP. Thank you.
Okay, so that.
Okay, thank you.
I have a question.
Yes, please.
Okay.
Yes.
So, in the physiological sensing, we have to deal with windowing. So, for example, 30 seconds, we have to accumulate data for 30 seconds and calculate something. Can you deal with such a windowing?
So maybe it requires some real timeness and the currently our language can deal with timing control by, let's say, explicitly acquiring the the timer, timer, timer or clocks as an input. Okay. So, but the program written in such a way is a bit complicated. So we want to extend the language to deal with timing constraints more easy way. That is the future work. But is it possible in current language?
Thank you.
Okay, thank you, Professor Numawo and Professor Watanabe. I think we have enough questions for now, so we can proceed to the next talk. Thank you very much again, Professor Watanabe. So we can prepare to show the slides of the next talk.
Okay.
Thank you very much. Thank you.
Thank you.
So the next paper is while they're setting up their slides. The next paper is titled "Improving Geospatial Search Using a Graph Database in Uber H3." The presenters will be J. Renzo Monteo and Ervin Kian Paulus Padeas from Department of Computer Science, UP Diliman. Again, just a quick reminder, you will hear two beeps. The first beep is, it means you have 3 minutes left, and the second beep is your time is over, which is approximately 22 minutes. So you can start your presentation now. Thank you very much.
Hello, guys.
Hello.
Morning.
Yes, we can see and hear your slides and hear your voice. Thank you.
Hello, I'm Jay. So we're going to present our research on graph databases and an indexing system called Uber H3. So Kian can start.
Hello, thank you, Jay. Hi, I'm Kian Paderas. I'd like to start off this presentation by introducing the problem area that motivated this paper. So there has been a rise in applications that were a direct result in the surge of on-demand economy. On-demand economy refers to activities that fulfill demand via immediate access to goods or services. As you can see, the most popular area of concern for these startups deal with transportation and logistics. But as we all know, in the pre-COVID days, one of the major concerns with transportation is traffic. Left is a picture of a traffic in Moscow, while the right is an everyday scene in EDSA. With no major upgrade to transportation infrastructure of a country, these applications will keep on dealing with this kind of problem. There is a need of instant information about the general area, especially with real-time traffic information. Existing systems that tackle this mostly use a grid system to represent locations, like the geographic Cartesian coordinate system. But there are other alternatives to this in order to represent locations more efficiently, which we will talk about later. Spatial databases were created specifically to hold these types of data, but the popular ones tend to be relational databases. In the rise of alternatives to it, one such database system was created that leverages graph network instead. They are called graph databases. Which brings us to the main motivation of this study. We aim to leverage graph database and global grid systems in order to improve performance of spatial databases. We will now discuss some informational background for this study. Spatial database systems focus on implementing database management systems, or DBMS, to handle spatial information. They are used to perform specialized queries in order to analyze, edit, and present the spatial data with ease. Represents geographic data by its vector approach or the use of geometric objects. One such example of a spatial database system is PostGIS, which adds support for geographic objects to the PostgreSQL relational database. PostGIS was implemented as an extension, but according to the findings of Open Geospatial Consortium, it follows its simple feature access for SQL specification of storage and access model of two-dimensional geometries. OGC is a consortium that released a specification that aims to help generalize location data storage to insight developments for this sector. One of the better alternatives of location representation are the discrete global grid systems. They are used to partition the Earth into regions, abstracting locations within it for ease of operations. Depending on its topology, one can utilize geometric operations in order to get specific locations. It can also increase its resolution to capture finer partitions of the Earth's surface. One of the popular geometric shapes being used to partition are hexagons. This topology has a higher packing density, approximate circular regions, and equal distance from other hexagon neighbors. Partitions will have only one distance between the center point and its neighbors with the hexagon shape. One popular example of this is Uber H3, which is a DGGS that partitions the Earth using icosahedrons. Then inside the icosahedrons, they follow the hexagon partitioning topology to create grids inside them. There are bindings available for different programming languages, and they are enjoying continuous updates up to this day. Although a study shows that it fails to meet all of OGC's specification for DGGS, uh, the same study showed that they were able to fulfill some basic DGGS functionalities in order for it to be usable in production use cases. Graph databases came from NoSQL database, which are used to offer real representation of graph relationships compared to implicit connection of nodes found in relational databases. The relationship between nodes are easier to query in this way, as it is stored directly without constricting it to a predefined model. These graph databases were able to utilize graph network relationships in order to run complex operations easily. One existing tool for this is Neo4j graph databases, which is an open source graph DBMS with good accessibility for various languages. It is based from a NoSQL background, and it is able to provide ACID-compliant transactional backend. It also offers native implementation of property graph model with the use of Cypher-query language. A general overview of our methodology. Most of our experimentations were done on a Mac OS machine, and our collection and pre-processing scripts were written in Python, and we are using PostgreSQL with PostGIS for relational spatial database and Neo4j with modules installed for UberHT and OpenJDK for our graph spatial database. For our data collection, we have utilized OpenStreetMaps and Google Maps in order to create a dataset for this research. We focus on acquiring locations with spatial amenity types describing it. We also have created a geofence surrounding Quezon City in order to bound our dataset. This location was chosen for its ease of access and familiarity for us researchers. We also defined our dataset to store only the amenity type, name of location, as well as the longitude and latitude of its area. The set of amenities from both Google Maps and OpenStreetMaps were then merged in order to create our dataset. For pre-processing, we have utilized the Places API feature of Google Maps as a cross-reference for additional information in order to eliminate duplicates and ensure that all of our rows have sufficient data. After pre-processing, the original count of our database comes to 19,148 rows. In order to see its impact on having a large dataset on its query performance, we've applied naive random oversampling to the dataset. This brings our dataset to 516,996 rows. Jay Renzo will discuss further about our experimental setup and the results of this study.
Next, please. So for our experimental setup, so the PostGIS setup is pretty straightforward. Just need to we just needed to import the CSV to the PostGIS local setup. But for the Neo4j, since it provided a desktop application which allows for a quick setup of the graph database, and also it provides a query language called the Cypher query language. So we set up a Neo4j database locally and then defined the amenities as single node and also defined a type node, which is the type of amenity. So the amenity consists of a name, type, and the longitude and latitude values. And then next, please, next slide. So this is the code for importing the dataset in Neo4j. So the last part, we defined a relationship between amenity and type. Next, please. And also for Neo4j spatial, we need to convert the latitude and longitude points to a point object. So the first code is the point conversion from the latitude and longitude to a point object in Neo4j. So we set the coordinate reference system as WGS84. And then for H3, we added the hex address procedure, which converts the latitude and longitude, and then we supplied a resolution value. So we arbitrarily chosen 9 as the resolution value. This will convert the latitude and longitude to the hex address in H3. And also we added an hex address property to the node, to the amenity node. And then lastly, we created an index on that hex address. Next, please. So for the bounding box search in Uber H3, we defined a function called polygon search, which accepts 4 location points. And then it will use the polyfill method from the H3 API to get all the hexes and all the points within that hexes. Next, please. For the Neo4j spatial, it's pretty straightforward. We just need to perform a query for the bounding box search. Same for the PostGIS search query. So we made use of the make envelope function from PostGIS to perform the bounding box search query. So for our results, so a total of 10 search queries are performed. So for each query run, 10 bounding boxes are randomly generated. So each bounding box search are executed in all 3 setups. So the first setup is the PostGIS, and the second setup is Neo4j spatial only, and the third setup is Neo4j with the integrated Uber H3 indexing system. So surprisingly, we achieved the lowest execution time on the PostGIS setup. So we may think this can be attributed to the GIST index of PostGIS. But upon performing a next slide, please. So upon performing the experiment on the larger data set, which consisted of 500K location points, we noticed that Neo4j with H3 performed the best with the average execution time of 2.2. Next, please. So we were able to produce the working implementation of a graph database with H3 as the indexing system, and also Neo4j graph database with H3 integration performed better compared to the native spatial Neo4j plugin. And compared to relational database like the PostGIS, graph implementation of spatial databases perform better at scale. So as part of our future work, we plan to perform more tests on bounding box search. So we will try to add more points in the polygon or perform route analysis. That's it.
Okay. Thank you for the presentation, Irvin and Jay. You actually finished earlier than the given time. So I think instead of the usual 2 to 3 questions, we can maybe accommodate about 3 to 4 questions. So let me check the question and answer box. Again, just a reminder to the panel members of WCTP 2020, you can, I think, directly use your microphone to talk and ask your questions or give comments and suggestions. So any questions now for the audience, for the guests, you can again type your questions in the Q&A box. Let me check. And at the moment, there are no questions or comments from the guests and the panel members. We have 34 attendees and 26 panelists at the moment. So let me Any questions? The panelists or the from the guests? Let me check. Okay, we have a question now from Orvin Liantos. How do you do oversampling for generating synthetic data? Can you Jay or Irvin answer? The question again from Orvin Liantos is, how do you do oversampling for generating synthetic data? Any suggestions, comments or answer? Irvin and Jay?
Hello.
Yeah, please.
Great.
I think this question refers to synthetic data, but you used synthetic data as well as real world data. Is that correct? And maybe how do you do, or how you managed, or how do how did you handle oversampling? Maybe that is part of the question of Orvin. Any thoughts on this?
Sorry. So for the oversampling, so first
Mhm.
in the first 20K data set is really real data from Google Maps and Open
Yeah.
OSM.
Yeah.
But upon performing the initial experiment, so we noticed that the PostGIS performed best. So we tried to oversample it using naive oversampling. And
Okay.
then yep. So we tried to oversample it to 500K, and then I noticed that the graph database with H3 performed better on the 500K data points.
Okay. So you used all of your data is from Google OpenStreetMaps or Google Maps?
We combined both data.
Both data from OpenStreetMaps and Google Maps. Okay.
Yep.
Yes.
Thank you. Any other comments, suggestions? We can take in 2 to 4 more questions depending on the length of the question and the reply. We have another one also from Orvin Llantos. Is the algorithm using naive oversampling available in the paper?
Currently,
Irvin?
we did not include it, but we only use the Python sklearn naive oversampling method.
Okay. So to implement the naive oversampling, you used an existing Python API or a code?
Yeah, from the sklearn library.
Okay, thank you. So I will answer this, reply this as answered. Okay. Any other questions or comments from the panelists or the guests? Let me check again. And I think just some quick question or comments, Irvin and Jay. This your work is open source, right? So this is the source is available in. I'm not sure. Maybe I missed it, but it is available in some repository. Is that correct?
We currently have a repository, but it's still private, so we can share
okay.
it.
Okay. So
Okay.
should somebody be interested, the code is available upon request. Okay.
Yep.
Okay. Thank you. We can. Any other questions from the panelists or the guests? Let me check the Q&A box. Okay, at the moment we have none. Another follow-up question. I think this is from this is your work with Dr. Figueroa. Is this a continuation of a previous project of hers, or a work of hers, or this is something that this just has been started the past year or so?
This is the first attempt to create a graph database with H3.
Oh, okay.
So, yeah.
With H3, but has Dr. Leia worked on other tools or technology before for graph databases that you may have referred to or cited in your paper?
Not yet.
Okay.
Yeah.
Graph database. Okay. Other questions or comments from the panelists? I think we can take in 1 to 2 more questions. Let me check again. The question and answer box. Okay, there are no. Oh, okay, sorry, there are no questions yet. Okay, I think at this point, if there are no more questions, we will thank the speakers. Irvin and Jay, thank you very much for presenting your work.
Thank you.
Thank you.
Thank you.
Good morning. So we can, according to the program, we can proceed to talk 3. So can the speaker for talk 3, can you please start sharing your slides? Brian Kenneth De Jesus, I think is this the speaker.
Francis, I'm setting it up.
Okay, thank you. So I will introduce Brian while he's sharing his screen. So the title of the next talk is an alternative method of analysis of quantum decoherence. The speaker is Brian Kenneth De Jesus with Henry Adorna as a co-author from the Department of Computer Science, University of the Philippines-Diliman. You have about 22 minutes. You will hear 2 beeps. The first beep it means you have 3 minutes left, and the last beep is that the time has run out. So you can start now. Thank you very much.
Thank you, Francis. Morning, everyone.
Morning.
So I'm presenting this paper, an alternative method of analysis of quantum decoherence. So first, we go to a short and quick comparison of classical computers versus quantum computers. Okay. So in terms of the physical nature, classical computers, as we know, uses registers that conform to classical physics. So we use bits here. But for quantum computers, we utilize the quantum behavior of atoms or low, small atoms or subatomic particles. Okay. So one advantage of quantum computers is, as opposed to a classical one, would have a fixed state, which is a 0 and 1, but a quantum computer would have a superposition of states, meaning that there's a probability that it will be a 0 and probability that it's a 1 combined, and that information is superior to a binary position, binary level of information. So potentially a quantum computer would have more information stored because of the superposition. So a classical computer has one advantage though, because it's 0 and 1, it can have a defined state boundary. So for example, a voltage level, on and off switch. But for quantum computers, since we're dealing with subatomic particles, we're dealing with actual properties of the subatomic particles. And inherent with the subatomic particles are decoherence. So it's a property in which the information is lost. So we are trying to, what this paper is trying to is look at the effect of decoherence on our algorithms or running time of the algorithms. Okay. So just a brief idea of what decoherence means. So one cause of decoherence could be external noise that affects the state of the system. So the quantum particles are very sensitive to external systems, and it's very difficult to isolate them. So an external noise would be a factor in decoherence. So second is, even if we eliminate external noise, if the isolated system can still evolve through time due to the probabilistic nature of the particles, and it can still evolve through time even without intervention. So we can still have some sort of loss of data after some time. So we have to run the algorithms fast. So with these problems, decoherence can still be corrected, but it's beyond the scope of this paper. So it would require another intervention. So some approaches to decoherence or past analysis of decoherence are included here. So one paper by Torrechete and Mons says that the rate of decoherence is proportional to the square of the register. So we can see that the bigger the register is, the larger the problem size is, we have an increasing rate of decoherence. So that's inherent. Another thing is by walls is the rate of decoherence is affected by the separation of states within the register. So if the states in the register have high variance of values, then the rate of decoherence is higher. So this aspect is not covered by this paper. And third is, of course, decoherence is hardware dependent. So it depends on the hardware or the particle that you're using. So there are particles that are more sensitive to decoherence, such as ions, and there are particles that are more resistant, such as photons. So there's an approach that looks at decoherence at a small scale. So the perturbative approach looks at it as small deviations per qubit level. So a coherence loss per operation can be defined per qubit as per Chuang's paper. Okay. So we are adapting Chuang's paper for our purposes because it is closer to our purpose of analyzing the effect of decoherence per operation, and therefore we can correlate it to the running time of the algorithm. So here's a proposed change in analysis. So in Chuang's paper, there's a given problem size and the number of operations, NOP, number of operations. And Chuang's approach is to compute the number of trials to be in the running time of the problem size times e raised to the power of the product, NOP, number of operations, alpha, which is the unit decoherence, and L, which is the number of operations. So it's sort of a generalized approach in which the number of trials is dependent on the number of steps and the problem size. So the proposed approach is to look deeper into the algorithm and look at the actual number of gates used. So the number of gates or the number of gates used is analogous to the number of operations. So instead of multiplying the number of steps times all the registers, we just count the steps in which there's an operation for that register. So here we have e raised to the n QOP, which is the number of operations times alpha. So note that we are using alpha, which is the unit decoherence, and we'll be using that variable as a basis of analyzing or checking if this algorithm is tolerable to decoherence or not. So let's compare our analysis of Shor's algorithm from Chuang's paper to the proposed algorithm. So for Chuang's paper, we have the register size and the number of operations defined here. The number of operations becomes L squared. For Shor's algorithm, it's known that the probability to get the correct answer after L squared operations is 1 over L. So the number of trials is in the running time of e raised to the L cube alpha. So if we compare it to the number of operations for classical, which is 2 raised to the L to the 1/3. So we compare the n trials and n op. And that's, if we compare those two, we get an alpha condition in which alpha must be less than 1 over L to the 8/3. So what does this mean? So alpha should be less than 1 over L 8/3 so that the quantum algorithm is preferable to the classical. Otherwise, if the unit algorithm alpha is greater than this number, then the quantum algorithm will be slower than the classical algorithm because of the number of retries that you need because of the information loss. So in this paper, we look at the actual number of gates. So this, we're looking at a quantum Fourier transform gate from Shor's algorithm and count the actual number of gates. So for example, in the last line here, M, L minus 1, there are L minus 1 phase shift gates. So if you see the dots below, there are L minus 1 phase shift gates, which is the X gates. And there's one Hadamard gate. And for the first line, M0, there's only one phase shift gate. So at line X, there's L minus X phase shift gates and one Hadamard gate. So we generalize that and sum that number of gates or number of operations in this summation here. NQO is equal to summation of 2L minus X plus 1 as X goes from 1 to L. And it equates to L squared. So once we compute the number of operations, we compare our method to Chuang's method. So if we look at the n trials line, so for Chuang's algorithm, L cube alpha is the number of trials. But for our proposed method, it's just L squared alpha. So there's a difference by a factor of EL, sorry. And if we compare it to classical, then our alpha condition is actually smaller. So it is possible that the alpha condition for Shor's algorithm is much smaller if we use that circuit. So why is it sort of better? It's because if we look at the circuit, it's relatively sparse. So there are actually less operations than anticipated. So Chuang's algorithm assumes that there's operation in each step. But if we look deeper, the number of operations, it's much less. So we can theorize that the alpha condition or the decoherence is much more tolerable for Shor's algorithm. Okay. So next is we look at two different algorithms and check if the alpha would be different. Okay. So probably we can predict that if we use different algorithms, the alpha conditions will be different because it will employ different circuits. So this next section will try to demonstrate that. Okay. So for Ettinger and Hoyer's algorithm for the dihedral hidden subgroup problem, so from their paper, we apply that algorithm. We look at that algorithm and apply our analysis. So the algorithm uses the same quantum Fourier transform as Shor's algorithm. So we therefore will have the same number of operations here. The only difference is that the probability of getting the answer, the correct answer, is different. So P is equal to O 2L minus 1 over 2L. So the number of trials will then be O, sorry, something's blocking. So the number of trials is OEL squared alpha sorry, you can see. Good. So we'll go forward to comparing it to the classical, and then we get an alpha of 1 over 2L. So for Kuperberg's algorithm, it solves the same problem of the hydral hidden subgroup problem. We uses DH. It uses a different number of operations, 2 raised to the square root of L, and the probability is close to 1. So we can assume it's 1. And the number of trials is E alpha 4 raised to the square root of L. So we compare it to the benchmark, which is 2 to the L over 2 classical. And therefore, the alpha condition would be should be less than L over 2 over 4 to the square root of L. So we go to a table to compare them to the two algorithms. So for the same register size, the number of operations is different. So for Ettinger, it's quadratic, but for Kuperberg, it's exponential. The probability for large L, we can assume it to be close to 1. So it's a very high probability. And the number of trials would be different, of course, based on the number of operations. So it's L squared alpha for Ettinger-Hoyer's algorithm, and for Kuperberg, it's alpha 4 raised to the square root of L. So we compare it to the classical, and the alpha conditions is different. So for Ettinger-Hoyer, it's an inverse, but for Kuperberg, it's L over 2 or over 4 to the square root of L. So for large problem sizes, we can see that Kuperberg will have a higher tolerance for decoherence. So I put it in a graph so you can see it visually. So it's a rough, would be a rough estimate of the comparison. So since we assumed a large L, we can look at the graph at high values of L, and we can see that Ettinger's algorithm will have a high tolerance for decoherence. So finally, another aspect we can look at is what is the effect of a distributed algorithm over a decoherence, on decoherence. So we're looking at Grover's algorithm, compare it with distributed Grover's algorithm. So the difference between these two is for Grover's algorithm, we use one monolith of all the search space, and for distributed, we divide the search space into P partitions, and then we search it individually. So as we can surmise, we dividing the problem size into smaller chunks, we can sort of predict that the decoherence will be much less for smaller problem sizes. So we're here to demonstrate that. So Zalka has expounded upon Grover's algorithm by making it distributed. So we divided the problem into P partitions, and the result here. So apologies, it's a quick jump to the result. The alpha is computed here. So if you can see, the tolerance is much smaller to Grover's quadratic speedup. So let's jump to a table to do a quick comparison. Okay. Oh, sorry. We do the computations first. So the number of partitions is roughly here stated here, and the number of trials is computed here. So if we can see the number of trials, we can focus on the term e raised to the alpha L 2 raised to the L over 2 over square root of p. So that is the largest term for this expression. And if we compare that to the classical, which is 2 to the L, then the alpha condition would be square root of p over 2 L over 2. So it's not much different from the classical monolithic Grover's algorithm. So if we compare the distributed versus monolithic, so let's go through the end. So we use the same number of computations or the same approach. The only difference that there's number for distributed is divided into p partitions. So the alpha condition for Grover's algorithm is 1 over 2 to the L over 2. And for distributed, there's a little bit of tolerance by a factor of square root of p. So we can attribute that not because of the distributed nature, but basically we divided the problem into smaller problem sizes. And because of the smaller register size needed, the coherence is expected to be less. Okay. So based on these three analyses, we have some conclusions. So the model of the coherence that we're looking at now, so based on the actual implementation, a model of decoherence is proposed based on the actual number of operations or the actual number of gates used. So that has been shown when we were analyzing Shor's algorithm. So secondly is if we compare two different algorithms, Ettinger and Hoyer's and Kuperberg's DHSP solution, different algorithms will have different tolerance for decoherence. So not depending on the problem size, but specifically the number of gates or the number of operations that will be used for that algorithm. And third, to look at the effect of distributed algorithms. As predicted, distributed algorithms are inherently better with decoherence, mostly attributed to the smaller size or subset problem size. Okay. And with that, we can go to any questions that you may have.
Okay, thank you, Brian, for the presentation. Now we can have about 2 to 3 questions for Brian in his presentation. Again, for the audience or guests, you can type your questions in the Q&A box. For the panelists, you can directly use your microphone, I think.
Okay. May I ask a question?
Yes, please.
I'm Shinya. I'm Shinya Nistek from Tokyo Tech, Tokyo Institute of Technology. One question is written on the chat, so please refer that too. And when you look at the algorithm, for example, you can somehow imagine the computational complexity of the algorithm. How is the coherence tolerance of the algorithm based on the experience of you're studying the coherence tolerance of some algorithms? Is it now possible to intuitively predict the coherence tolerance of an algorithm? You can imagine or guess the coherence tolerance if you see some given algorithm. For example, could you
Yes.
Could you give me some comments on that?
Thank you.
Okay. Yes. So given a specific algorithm, so once we know the number of operations, so visually it can be seen by looking at the circuit. So as I shown earlier in Shor's algorithm, I look at the circuit. So visually that's what you can do, but you can also look at the operations being used. So we count, I think it's easier to explain that if you count the number of gates in the entire circuit, we assume a certain number of decoherence per gate. So that would be alpha, right? So alpha is an abstract description of decoherence, taking into account possibly external factors, the hardware used. So that alpha will represent the decoherence per gate, essentially sort of the quality of the gate. And that once you build the entire circuit, we can sort of predict the coherence for the entire circuit as a function of alpha. So the coherence would affect the result, the probability of getting the correct result. And if the probability gets low because of the coherence, then we need to, retry the operation again, and that would effectively increase the running time. So bad alpha would result into more decoherence, which would result to a invalid result, and then it would result into retrying the algorithms again. So retrying would result into a longer running time.
Okay.
Thank you.
Thank you for the question, Professor Shinya, and for answering, Brian. I think we can have one more question. Let me check the question and answer box, or from our panelists. Okay. I have a question, Brian, because the title of your paper and presentation is Alternative Method of Analysis of Quantum Decoherence. However brief, can you give the idea of the main difference of your alternative method for analyzing quantum decoherence? Because I think there is some, as Professor Sinyo mentioned, in your slides showed, there are some interesting differences in terms of time complexity and in your conclusions as well. So can you briefly give the idea of what is different in your alternative method for quantum decoherence? Thank you.
Okay.
Maybe okay.
So the basic difference is we are jumping off from Chuang's approach, in which the analysis is based on the number of steps times the problem size.
Okay.
So if we look at the circuit, so it's actually easier to present it visually. So if you look at the quantum circuit we're using for Shor's algorithm, Chuang's paper assumes that for each step, so here we have, if you look at the first step, on the leftmost, there's a Hadamard gate. So Chuang's assumes that there are L squared steps. So starting from that Hadamard gate, the next step would be x1, and the next step would xl minus 1. So he counts the number of steps, and then he counts the number of registers, which is L. So that simple product, steps times the number of products, would be the number of operations.
Okay.
So Chuang's paper assumes that the number of operations is a product of that. But if we look at the circuit in detail, the number of operations is actually much less, because specific to the QFT, the number of operations is very sparse. So if we look at the first step, there's actually just one operation and not L operations.
Okay.
So this paper proposes that we analyze it this way.
Okay.
So there are actually algorithms that has more gates. So for example, a Grover's algorithm, it's there's more gates. So Chong's analysis is actually better analysis for that because the circuit is full of gates. But
Okay.
we can look at Chor's algorithm, and this is an instance in which this proposed method of analysis could be better or could be more accurate
Okay,
potentially.
thank you. Okay, thank you, Brian. I think at the moment there are no questions in the Q&A box, as well as from our panelists, and we're actually still on time, more or less. So thank you very much, Brian, for the presentation. According to our program now, after the talk by Brian De Jesus, we have a 10-minute break. For those of you who want to stretch or go to have a toilet break. Time check now, Manila time is 25 minutes past 10, so 10:25 a.m. We will resume after 10 minutes, so that is 10:35 a.m. So hopefully you will still come back and listen to we have 3 more talks after the break and before the lunchtime, another lunchtime break. Thank you very much and see you in about 10 minutes. Thank you, Brian.
Thank you. Thank you, Francis. Thank you, everyone.
Okay. Joyrene, I think Joyrene Clemente is here. Can you hear us?
Hello, Francis.
Hello, good morning. So thank you. Just checking on Joyrene. So we can now begin resuming the second session, the second and last session of the morning session for WCTP 2020. Thank you very much. So the second session will be moderated by Dr. Joyrene Clemente from the Department of Computer Science, University of the Philippines-Diliman. Thank you very much, Joyrene, and please you can start the moderation now using the program. Thank you very much.
Okay. Thank you, Francis, for the introduction. Hello, once again, I'm Joy Clemente, and I'll be moderating for the remaining paper presentations for this morning. Welcome again to the participants of WCTP 2020. We have 3 more papers before we have our lunch break. So just a reminder for everyone attending to this workshop, we have 20 minutes presentation for all the papers, and then we have 5 minutes for the Q&A. So you can post your questions using our Q&A box, and then we will go through each of your questions after the paper presentation. So I guess without further ado, we can start with our paper number 4. So effect of quantum decoherence on the Deutsch-Josa algorithm, presented by the authors, Luis Gabriel del Rosario et al. So I think, Luis is here, so go on, Luis.
Hello, good morning. I'd like to ask if the microphone is clear enough.
Yep, you can hear you, and we can also see you.
Okay, I will share my screen. Okay, can you see the slides?
Hello, Luis, not yet.
Okay, wait. Oh, there, okay. How about now?
Yeah, we can already see your slide. Okay.
Okay.
Thanks.
So I'll start. Good morning. I am Luis Gabriel del Rosario, and I will be presenting our research entitled Effect of Quantum Decoherence on the Deutsch-Josa Algorithm. So just a quick overview of what I'll be going through. I will first talk about a brief introduction about quantum computing and some preliminaries. And then I will go over the Deutsch-Josa algorithm, as well as how decoherence could be represented mathematically and computationally. Finally, I'll go over the results, the analysis of the effect of decoherence on the Deutsch-Josa algorithm, and I will go over the conclusion. Just a side note, I will be, for the preliminaries and some other parts of the background, I will be sort of going a bit quicker in order to be able to make it into the given time frame. Okay, so an introduction. As classical computers become more and more advanced, they start to reach their limits. Components such as transistors get smaller and smaller, and they start to exhibit quantum mechanical properties. Now, these properties could be taken advantage of for computational purposes, and that's exactly what quantum computers are doing. So these quantum computers take advantage of the anomalies of quantum mechanics. So one main difference is that instead of a classical bit that stores information that's either 1 or 0, it makes use of what we call a quantum bit or a qubit that can exhibit quantum mechanical properties such as superposition or the ability to be in both the state 0 and 1 at the same time, and entanglement, where one qubit measurement could affect the measurement of a different qubit. So quantum computers can solve certain problems exponentially faster than classical computers. And one example of this, one of the first examples of this, is the Deutsch-Josa algorithm. What this algorithm does is it solves a very specific black box problem. A black box problem being you are given, well, in simpler terms, you're given an input and an output, and you have to try and guess what operations are done in between the two inputs and outputs. So the classical solution of this algorithm is has a time complexity of O of 2 raised to n, while the quantum algorithm theoretically has the running time complexity of O to 1. So as you can see here, it's a very vast difference between the classical problem and the quantum computing and the quantum algorithm. So this algorithm is used as an example of how quickly quantum computers can become. So a problem with quantum computing is that research on these algorithms assume a perfect quantum system. However, this is not the case because information stored in qubits is quite fragile, and that information can be lost through unwanted interaction with the environment. And this is called quantum decoherence. So recently it's been starting to be considered into the design and analysis of the quantum algorithms. And moreover, some methods, including Chuang and De Jesus's revised method, are easily applicable to other algorithms. So the Deutsch-Josa algorithm is one of the most simple and trivial examples of the exponential speedup between quantum and classical computers. However, as I mentioned, it was designed without decoherence in mind. So then we must ask, which parts of the Deutsch-Jossa algorithm could lead to decoherence? Moreover, how tolerant is the algorithm to decoherence once we get a numerical value for the decoherence of the algorithm? So the objectives of the study are as follows. So through this study, we aim to achieve we need to compute for the numerical value for the decoherence of the Deutsch-Jossa algorithm using the method introduced by Chuang and refined by De Jesus as presented earlier. And we need to empirically demonstrate how the obtained value affects the execution of the algorithm. So then we can relate the value obtained to the decoherence of other algorithms like Shor's factoring algorithm or Grover's algorithm. So determining the decoherence could show the tolerance for faulty quantum computers. And this is especially important when quantum computers start becoming commercialized. And yeah. So then once we are able to use this method, we can also set standards for the realization of the quantum computer. And we can also determine a relationship between the simplicity of the Deutsch-Jossa algorithm and its decoherence, and see how it pairs up with other more complex quantum algorithms. And finally, if we are able to use a single method with multiple algorithms, we can eventually come up with a sort of hierarchy between these algorithms based on decoherence. So as I mentioned, I will just be breezing over these preliminaries, but for those who are not familiar, a qubit is mathematically defined as a unit vector in a two-dimensional Hilbert space. And the state of a qubit is denoted using the Ket notation. The values alpha and beta here signify how probable it is that the qubit will collapse to state 0 and how probable it is to collapse into state 1 respectively. Note that the actual probability is that you square the values of alpha and beta. And in order to move or modify these quantum states, we use quantum gates. So examples here are the Hadamard operation, the identity matrix, and the Pauli X gate. It's worth noting that the quantum gates need to be unitary. So, and this will come up also later. And finally, for entanglement, the measurement of one qubit will ensure the measurement of another qubit. So a common example here is the controlled NOT gate. However, this does not show up in the Deutsch-Jossa algorithm. So let us discuss this algorithm. So the problem is as follows. We are given a function f, which takes an input of n length, and each value could be either 0 or 1, and it maps it to an output that is either 0 or 1. And this function is promised to be either constant, which means that for any input, it will either map to 0 for all of them, or it will map to 1 for all of them. So it could be that, or it could also be balanced, which means that the chances of getting 0 for any input is equal to the chances of getting 1. So it's a 50-50 chance depending on the input. So without looking at the function f, determine whether the function is constant or balanced. So classically, how would we approach this? The first thing that would come to mind would be a brute force approach, wherein you look at the entire domain and look at the output in order to check if it's constant or balanced. And it says here that the domain is 2 raised to n. And so we can already see that the time complexity of this would be O of 2 raised to n, because you're going to be brute forcing the entire domain set. So, however, in terms of actual computations, you can only look at about half of the domain plus 1 in order to be certain whether the function is constant or balanced. So what you do is you look at half of the domain and 1, or more than half of the domain rather. So if all the values are 1, or if all the values are 0, then the function is constant, else the function is balanced. This is sort of a bit more optimized compared to when you brute force the entire domain, because here you only need to look at half of the domain. So lemma number 1 would be that the number of steps needed to solve this algorithm is 2 raised to n minus 1 plus 1. That is 1 more than half of the domain, which is 2 to the n. And lemma number 2 would be the time complexity, which is the class of O of 2 raised to n. And so we have an example here. We have a function that is x1, xor x2, xor x3. This takes in an input string that of length 3, and it maps the output to either 0 or 1. So as you can see here, this function is balanced because for exactly half of the domain, 1, 2, 3, 4, it maps to 0, whereas in the other half of the domain, it maps to 1. And if we follow the example here, we only need to check five of the values instead of all 8 in order to conclude that the function is constant or balanced. In fact, if we look at it from top to bottom, we can see that the first output is 0 and the next output is 1. And we can actually stop there because we are sure that if it's constant, then all the output would be the same, except in this case, it's different. So if we were to convert this into a quantum circuit, the function f alone is not unitary and thus cannot be inserted into the quantum circuit. And so we make use of what is called a quantum oracle function, which basically what it does is it takes a classical function, a classic mathematical or Boolean function, and it sort of, 8 minutes remaining, I'm sorry. And it maps it to the input. And it puts it into a quantum circuit. So what this does is it makes use of a set of input bits and a garbage or ancilla bit where we would store the output of the function f. And also in the input gates would be modified as such as well. And so this is the quantum circuit of the Deutsch-Jozsa algorithm. So what we do is, the steps are, first we initialize each qubit to 0 and the ancilla bit to 1. And then we apply the Hadamard gate to each qubit, and we apply the oracle function to each qubit. Then we apply the Hadamard gate to each of the input qubits, and then we perform a measurement on each of the n qubits. Measurement basically means that we collapse the superposition of the qubit. And I will actually just skip over Cleve et al.'s description of this. But basically, in order to check if the function is constant or balanced, then we only need to check that if the amplitude, the probability of getting all 0 is 1 or 0. So basically, we only need to perform one measurement. And if that measurement is 0, then we know that the function is balanced. Else, if the measurement is, or rather, if the measurement is 0, then it's constant. Else, it's balanced. So here we see that only one measurement is necessary. Okay, I will just be going a bit faster now since I have less time. So decoherence was explained by Mr. De Jesus earlier. So I will be just going directly to Mr. De Jesus's method here. So here I just described Chuang et al.'s method, but Mr. De Jesus, he made his own modifications to the algorithm such that instead of using assumptions to count the number of operations in the quantum algorithm, we count it manually. Okay, so in order to get the actual unit decoherence of an algorithm, we need to compare the number of steps needed to get the classical algorithm and the number of steps needed in the quantum algorithm. And in order for there to be a point to use the quantum computer, the number of steps in the quantum algorithm needs to be less than the number of steps in the classical algorithm. And from this inequality, there's a value called alpha, and that alpha, we can actually get a numerical value for that. And so the alpha would signify at what amount of decoherence would the quantum algorithm be less efficient or just as efficient as the classical algorithm. So the first theorem is that the Deutsch-Jozsa algorithm is bounded by alpha, L over 3L minus 1. And so we just plug in Mr. De Jesus's method. to get the value L over 3L minus 1. And there we can, from Chuang's paper, we can also get the largest input size, which is this value. And okay, so given this, what we can do is see the trends with how much, if what happens when you add decoherence. Will it become more error prone? Will it become more efficient? Things like that. So what we did was we simulated the algorithm using NumPy. So what it does, it takes a function mapping, and it determines whether the function is constant or balanced. So what we did here was, okay, so we can see in the quantum circuit that the oracle function is what is what interacts with the environment. So we can say that it's the weak point of the system. So what we can do is we can mess with the input to the program to simulate decoherence. So what we did here was we introduced decoherence to a constant function by messing with the input. And as you can see, with decoherence, the probability of getting 0 is less. And there are chances now of getting other values that are not what we want. Same thing here with the balanced function. And this is, although the probability distribution here seems very chaotic, the value, the probability of getting 0 is still 0. So it is still a balanced function. However, when we introduce decoherence, there is now a chance of getting 0, which would lead to a wrong result. If we graph alpha in terms of register size, we can see that it approaches a limit of 1 over 3. And so we can say that with maximum register size, with an infinite register size, the maximum decoherence we could have is 1 over 3. And so with decoherence, we can actually get error. And as I mentioned earlier, error would be the probability of getting the wrong answer. So with constant functions, it is the probability of not getting 0. And with balanced function, it's the probability of getting 0. So here, what I did was we graphed the probability of error with increasing levels of decoherence. And with our maximum alpha boundary of 1 over 3, we could get the maximum error that we could achieve before the quantum algorithm becomes less efficient than its classical counterpart. And we could see here that once the error reaches around 55.56%, then it is around just as efficient as its classical counterpart. So this means that if the system gets the wrong answer half of the time, it will still be much more efficient than its classical algorithm. Or not much more, it will be more efficient than its classical algorithm. And so we compare also the graphs of alpha for Deutsch-Jossa's algorithm with other quantum algorithms like Shor's and Grover's algorithm. We can see that the other algorithms, the tolerance for decoherence approaches 0 as the register size, as the register size increases. And so we can see that the Deutsch-Jossa algorithm is much more tolerant to the quantum algorithm because it approaches a certain value, implying that even with an infinitely large register size, there is still tolerance for decoherence. And so here's just a summary of the tables of the results that we computed for alpha. As seen in the figure, the decoherence of the other two algorithms approach 0, as I mentioned. So there comes a point where there is no tolerance for decoherence for the other quantum algorithms, while the Deutsch-Jossa's algorithm approaches 1/3. So in conclusion, these are the summary of my results. The decoherence boundary where the quantum algorithm will become less efficient than its classical counterpart is L over 3L minus 1, where L is the register size. And the maximum error that we can get when we're at that boundary is 55.56%, implying that even when the quantum algorithm has enough decoherence to get the answer wrong half of the time, it is still more efficient than the classical counterpart. And the largest input size would be this. So for further research, I recommend applying this method to other quantum algorithms and experimenting on actual quantum computers. as it will be shown later in a presentation later that there are other ways to simulate decoherence, and these trends that I showed you earlier would also be exhibited in that paper. So that is all for me for our presentation. Thank you very much.
Thank you so much, Luis Del Rosario, for that wonderful presentation. The floor is now open for question and answer. So our first question is from Professor Shinya Nishizaki. So you mentioned that the Deutsch-Jozsa algorithm is better at resisting decoherence compared to Shor's and Grover's algorithm. Is decoherence tolerance difficult to achieve? So for example, is it possible to modify the Deutsch-Jozsa algorithm to further improve the decoherence tolerance? So let's start with the first question. Is decoherence tolerance difficult to achieve?
Well, I think there are ways to mitigate the decoherence in an algorithm by modifying the actual circuit. However, when it comes to modifying the circuit, if we modify it too much, then it might not yield the same results as what was intended when the algorithm was originally designed. So when it comes to decoherence tolerance by modifying the circuit, I think that the focus needs to be more on other factors, such as when it comes to the actual realization of the quantum computer, like in its hardware, in the technology needed to maintain the quantum state of the qubits, things like that. For example, is it possible to modify the Deutsch-Jozsa algorithm to further improve the decoherence tolerance? I think there are ways, except it won't be it might deviate from what it was originally intended to do. And there are other ways apart from modifying the circuit to mitigate the decoherence usage. And the first thing that comes to mind is when it comes to building the quantum computer, because I'm pretty sure that the research scientists that are developing actual quantum computers are keeping this in mind, that the qubits need to have as little interaction with the environment as possible. So the technology that they develop for that needs to be robust and coherent.
Thank you.
Okay, thank you. So Shinya, is that okay?
Okay.
Okay.
Thank you,
Okay,
sir.
so in the interest of time, we can still accommodate one more question. So we received a question from our Q&A box from Orven Lantos. Interesting presentation. Can you recommend a playground on learning how quantum computer works?
Okay, so hold on. There are actually a lot of resources online for that. For example, IBM, I actually forgot what it's called, but IBM has a lot of resources in learning about quantum computing. And they also have an actual quantum computer that's for lack of a better term, it's open source. So you can like hold on, IBM Q, I think that's it. There, yes, IBM Q. You can design quantum circuits and have it be run in IBM's quantum computers. And then you can actually because their quantum computers are very famous, a lot of people are trying to access it. So what you can also do is run it on a quantum computer simulator. And actually, I think their simulator also runs pretty well because the quantum computer that they open to public is only 5 qubits large. So a simulator would be able, a powerful computer would be able to handle that kind of stuff. So there's IBM Q. There's also, I think there's also Qiskit. Yes, Qiskit is also another company that has resources for learning quantum computing, and for they actually have a simulation library in Python, so you can use that. So there, they have access to circuits, they have hardware access, and they have research on quantum algorithms and things like that. Noise mitigation. Here, this is a form of decoherence mitigation. Yeah. Yeah. So you can check out things like the IBM Quantum Experience or Qiskit, and they have a bunch of resources for learning how quantum computers work and for executing your own quantum computers. Here, actually, this is a pretty nice website. You have different learning levels for quantum computing. So you can code with Qiskit, you have a blog for it, etc. So yeah, I'll probably link these to the chat
Mhm.
for everyone to see.
Okay. Thank you. Thank you so much, Louise. So for those of you who are interested to start your research on quantum computation, probably you can try Qiskit and IBMQ to get to try how to code algorithms using quantum computers. Okay, so I guess again, let's all thank Luis Del Rosario for that wonderful presentation. And then we will proceed to our next presenter. And the paper is entitled Bounded Construction Types for Functional Reactive Programming. So the authors are Akihiko Yokohama et al. Okay, we can now see your slide. Okay.
Can you see my slide?
Yes, yes.
Yeah,
We can
okay.
also hear you. Okay. Thank you.
Yeah. Thank you. Hi, my name is Akihiko Yokoyama. I'm student of Tokyo Institute of Technology. Today, I will talk about recursive data types for a functional reactive programming language designed for small-scale embedded systems. This is an overview of what I talk today. The objective is to relax of restriction on recursive definitions in an FRP language designed for small-scale embedded systems. We overcame this issue by introducing the type with size information of the data structures and allowing the use of primitive recursive functions. Consequently, the structures commonly used in functional languages, such as lists or trees, can now be handled by natural representations. In addition, the amount of memory required at runtime can be statically determined by traversing syntax trees. As background, functional reactive programming, FRP, is a programming paradigm that describes reactive systems using time-varying values. Reactive systems are applications that continue to respond to input, such as GUI systems and animations and embedded systems. Such systems are typically programmed using polling or callback functions, but this kind of program code can be complex. Time-varying values are abstractions of values that change over time. For example, mouse positions or sensor readings. In FRP, we can sufficiently describe the system by declarative combinations of time-varying values. MFRP is an FRP language designed for small-scale embedded systems. This is also statically typed pure language. This is designed and implemented to work on tiny microcontrollers such as AVR. MFRP compiler can statically determine the amount of memory used at runtime. So it is suitable for embedded systems. This is an example of MFRP module code. This program calculates the expositions of the vehicle from the velocity of the wheels and the angle of the body. One of the features of MFRP is at last reference. When we refer a variable with at last, we can get the previous value of the variable. In this example, we compute the integration of the velocity by adding a small distance to the last value of variable x. We explain the execution model of MFRP. Each of nodes defined in the program is calculated in order. To compute the proper value, the computation are performed in the order of dependencies. In this figure, the blue node is the input node and get the input from the outside, input value from the outside. The gray node are the intermediate node and compute the value. The red node represents the output node and outputs the value to the outside. And the solid black arrow represents the reference to the last value, current value of the node. So the black dotted arrow represents the reference to the last value of the node. To run the program, the memory for current value of the node and the memory for at last value and temporary memory used for the node computation is needed. After each node calculation, it sets the current value as the last value and release unused memory space. MFRP performed reactive behaviors by repeating this iteration. But MFRP does not cause the time leak and space leak problem that are associated with FRP. It is also suitable for coding small embedded system because the amount of memory used at runtime can be statically determined. However, there are some restrictions to maintain these features, especially to simplify the determination of memory usage. The definition and use of recursive functions and recursive data types are prohibited. This problem is that data structures such as lists and trees, feature commonly used in functional programming programs cannot be represented naturally. In addition, it is difficult to handle a data structure with a dynamically changing number of elements, and the lack of code maintainability is also a problem, even if a static data structure. As a motivating example, consider the module DAP check. Which determines whether new input variable is contained in the last 4 inputs. The length of input history may be changed later. This program is the DAP check module in conventional MFRP. The module takes the input values V of type int and output the detect node of type bool. Opt-I type is option or maybe type for an integer value. History node represents the input history. Because MFRP does not support arrays, so this node uses opt-I type and fixed length tuple. In the history node, the previous history is shifted one by one, and the input value V is added to the history. The detect node decomposes at last value of the history and check if it has the same value as the input V. If there is a change in the history length, the area represented by red text needs to be changed. For example, suppose that the history length is changed to 5. Then we need to add the blue text. We have to edit all the parts that deal with the 5th element. Furthermore, when the history length changed to 6, it looks like this. Whenever the history length is changed, several parts of the program have to be modified appropriately. Because the history is decomposed as A1 and A2, it is easy to make mistakes in the variables. Such a program would be poorly maintained if written in conventional MFRP. But we want to solve the previous problem by managing the input history as a list structure. Note that if you introduce recursive data types and recursive functions without any restrictions, you can write programs that do not stop doing iteration or use an unlimited amount of memory. Therefore, we introduce a data type with size information to guarantee the termination of the computation and to compute the memory usage. We call such data types bounded construction types. We introduce a primitive recursive function to handle these data types. In addition, several new syntaxes have been introduced to MFRP. Below is the double-check module written in MFRP with this extension. First, we define this type in constructor N and C. Next, we define the helper functions for the list. Here, we define the insert function to insert value at the end of the list, and search functions to search for value in the list, and tail function to get a value other than the head of the list. During the function definition, the list type is assigned a size of m. Finally, we define the history node to represent the input history and the detect node to represent the result. The history node is defined as a list of size 5. In the history node, the new syntax called fit expression judged the size of the list and insert the input values at the end of the list if the space is free. Otherwise, it removes the head and it inserts them at the end of the list. In the detect node, the search function is used to compare values. If we implement the double-check module with the list in this way, when the history length is changed, only the parameter of the list length need to be changed. Even if there is a mistake in the changes, a size consistency check at compile time can detect the mistake. Bounded construction type BCTs are recursive data types with annotation about the size of the object. This annotation is called a size parameter. The size parameter represents the maximum size of its own constructors in the object. That is, the actual size of the object at runtime does not need to be exactly the same as the size parameter. By using the usual type information and size information, the upper bound of the object size can be determined statically. For example, the type of the tree structure is defined as shown in this slide. In this case, the instance of the tree 5 type has the structure shown below. Of course, in the case of list structure, the size parameter means the maximum length of the list. Our method statically checks type and size consistency, generate constraints on size parameter during type checking. For example, in recursive call of the function, an argument size decreasing is a constraint. Constraints are Presburger arithmetic expressions. Finally, we verify the validity of the constraints on size by checking satisfiability with an SMT solver. For example, we show the constraints obtained from the insert function used in the DAPCheck module. First, the size of constructor n is 1. The size of the constructor C applied to n is 1 plus 1. Then the size is then the size is cast by ADJ expression. That is, we get 1 plus 1 less than equal to 1 plus m as a constraint. Next, since L is a list of sizes m, the composition yield a constraint m equal 1 plus n. In addition, the argument decreasing is checked on the recursive call, and the constraint n less than m is obtained. Second, the constraints for each arm of the case expression are represented using the constraints we have generated before. During the decomposition of constructor, the constraints are added as a precondition. The red line equation is a constraint that the size of the result is the same. The constraints of the whole case expression are represented by conjunction of constraints obtained from each arm. Thus, the constraints shown here are obtained. Finally, using the constraint m greater than 0 given as a precondition to the function and the resulting size constraint, we obtain the constraint shown below. By checking the satisfiability of this expression, we check if the consistency with respect to size hold. In fact, this constraint can be satisfied. Our method determines the runtime memory usage on each node. The target memory area is the heap and call stack and local variable stack. By allowing only constant size parameter to appear in node definitions, so we can perform the traversal from node definitions. Compute the amount of memory needed at runtime by scanning the syntax tree while assigning size parameters. We discussed related works. First is size types. Size types is also include object size information in the types. BCTs are strongly influenced by the size types. Our BCTs are different in that we can change just the size of the object at runtime by using fit expression. The BCT's fit expression is better suited to MFRP's execution model and at rust behavior. For example, in the DAPCheck module, we judged whether there is a free space in the list by using the fit expression and performed an insertion operation on at rust value of the list. If we want to do this in the original size types, you need to create a list with multiple dummy values in advance. The second is raster. Raster is a synchronous data flow language. Fixed length array were introduced in raster v6. And arrays can be handled by built-in functions such as maps or fold. However, as with MFRP, it is not suitable for representing lists and trees. This is summary of my presentation. We introduced bounded construction types for MFRP. which is an FLP language for small-scale embedded systems. This introduction relaxed the restriction of the recursive definitions in MFRP. In our paper, we also give formal definitions of MFRP with BCTs and prove their soundness. Implementing compiler of MFRP with BCTs and measuring the compile time and runtime overhead remains a future task. That's all for my presentation. Thank you.
Thank you, Akihiko, for that wonderful presentation. The floor is now open for questions. Okay, so I am checking the Q&A box. We still have no questions from the Q&A box. I'm looking at the chat box. Okay, so we have a question from Masa Numau. It seems that a stream type can describe the duplication checking module. What is the difference?
Stream.
So this is just asking that in my experience, we a kind of stream data type can be defined, I think. So in the case of duplicate checking module, you are updating.
Actually, stream type is same as the list we.
That is a stream type.
Yeah, but maximum length is bounded. Maximum length is defined.
Can be defined. I see. Yeah, I understand. Thank you very much.
Thank you, Professor Numau, for that question. I also have a question for Akihiko.
Right. Yeah.
So I think this is fairly related to the streaming type that Professor Numau mentioned a while ago, but can we still use streaming data from IoT devices using this particular data structure, which is a bounded construction type for this programming model?
Up to.
Can we still use it for streaming data?
Streaming, yeah. In MFRP, all data type and input value is streaming data. So, this list I presented to the list is stream of stream.
As a follow-up question, perhaps I would like to know: how do you identify, for example, how do you identify the bounding parameter? For example, I would like to use this particular data type. Is it depending on the problem, perhaps, or depending on the type of input, or perhaps the limitation of the device?
Yeah, one more.
So for example, how do we identify the parameter, the additional parameter, which is the bound for the BCTs?
So you mean how to determine the size of data types?
Mm-hmm.
Yeah. So I think this may be somehow kind of, how to say, from experimental, that because of that, actually, so we can, it is possible to express the, let's say, so streaming kind data types. But so, for example, and we can define the bounded buffer inside the modules using these bounded construction types. But what to say? The size of a buffer can be the size of a buffer should be determined by some parameters like so. For example, so timing and speed and size of data, so and so on. So it is not easy to so determine the size of data, but so it should be some how to say
empirically obtained,
yeah,
perhaps.
yes.
Yeah. Okay. Thank you so
you.
much. Once again, we welcome and thank Akihiko Yokoyama,
Yokoyama, yeah.
Yokoyama, sorry, for that wonderful presentation. And we will go to our last presenter for this morning. And the topic is about the polarizing channel on the Deutsch-Rosa and quantum counting algorithm using Qiskit. And I think our presenter is Pio Fortuno. Okay. So, welcome, Pio.
Hello, can you see the slides and hear me clearly?
Yes, we can see the slides and hear it clearly.
Okay, so the earlier presentation by Luis, or Luigi as I call him, he co-authored part of this, so there will be a lot of overlap between this presentation and his. So yeah, the polarizing channel on the Deutsch-Josa and quantum counting algorithm using Qiskit. So yeah, here's the table of contents. The preliminaries have been more or less discussed already by Luigi and Brian earlier, as well as the Deutsch-Josa algorithm. So I'll breeze through them just as a quick refresher. So for the introduction, yeah, as stated before, transistors in classical computers are getting smaller, and then as they get smaller, quantum mechanical properties manifest. And we can use these properties for our computations. So yeah, quantum bits, qubits instead of bits for quantum computers, and then quantum algorithms can solve problems faster than classical algorithms, as seen before. And then part of the reason for this study is that most studies on quantum algorithms assume perfect quantum systems. So decoherence is a real problem here. Like, so there are a lot of studies trying to analyze algorithms and the effects of decoherence on those quantum algorithms. And each of these studies go about analyzing that decoherence in their own ways. So here, I also use Qiskit. I believe Luigi mentioned it earlier. It's a Python framework for quantum computing. Yeah, you can download it after if you want. It's really easy to learn. So the quantum counting algorithm finds the quantity of solutions, or M, to an n item search problem. So this study tries to see the effect of decoherence on the quantum counting algorithm. So there was a previous study by Hasegawa and Yura that performed a numerical analysis of the effects of decoherence on the algorithm. So I'm going to be using that as a basis for this study. So the objectives of the study is to create a method using Qiskit to simulate decoherence, and then determine the boundaries of allowable decoherence by the method that Brian De Jesus mentioned earlier. And then we apply that method to check out what happens. So the significance of the study will show the limits of these quantum algorithms, show the effects of decoherence on these quantum algorithms, and then show that there could be an easier method for simulating decoherence. So here's the explanations for qubits said earlier by Luigi, and then here are quantum gates that change the system over time. The poly X, Y, and Z gates are going to be significant here because those are the gates that will be used when simulating decoherence. I'll explain it later. And then here there's the quantum Fourier transform. It's the same as the discrete Fourier transform, except it's used in a quantum circuit. So if you're familiar with the discrete Fourier transform, the stepping stone to the quantum Fourier transform is really easy. So here's how the circuit looks like. So quantum phase estimation, it estimates an unknown. Wait, I forgot that. I forgot that Greek letter. If someone in the chat knows what it is, just mention it. On a unitary operator U with an eigenvector ket U to get its eigenvalue. So then we assume that we have an oracle or black box capable of preparing the state. Thank you, Phi. And performing the controlled U to the 2 to the J operation. So here's the circuit for the quantum phase estimation. Notice how there's U to the J. That's how many different that's the operation that many times. And then at the end, there's going to be a quantum Fourier transform, an inverse quantum Fourier transform, and the measurement right after. So Grover's algorithm uses that. Grover's algorithm, or the quantum search algorithm, it finds the index of a solution in an n-item search function. So for convenience, it's assumed that n is a power of 2. So the index can be stored in small n bits. And the search function has exactly m solutions, with the number of solutions being between 1 and the n problems inclusive. So this is how the circuit looks like. So there are O to the square root of n Grover iterations. So this is the Grover iteration. This is like an inversion about the mean. So I'll skip. I'll breeze through this. Basically, what it does is turns the measurement of getting a correct answer higher. It increases the chance of getting a correct index higher, while lowering the chances of getting the incorrect indexes. So this is the circuit of a Grover iteration. Yeah. You can see the phase circuit there. Yeah, so you'll notice this, and then afterwards the graph there shows how each of the steps change the amplitude of the qubit, and it wants to go closer to the higher amplitudes if it's the correct index. So how many Grover iterations should there be? So you'll notice that in these equations there is m, big M. So we need to know that, because m is how many possible solutions there are. So how do we find that? We use the quantum counting algorithm. So this section explains the algorithms that we're going to study. Since Luigi already mentioned the Deutsch-Jose algorithm, I'll skip this. So here for the counting problem, given an n-item search problem, what is the number of solutions m? So the two classical solutions are brute force and sampling, both of which have a constant runtime. I mean, not constant, have a linear runtime of O of n. So the quantum solution uses phase estimation and Grover iterations to estimate m with complexity of omega square root of n. So it finds the eigenvalues, e to the I theta and e to the I 2 pi minus theta based on g, which was the Grover iterator, which was for the Grover iterator before. So we assume we have an augmented oracle to have an expanded search space 2n, allowing sine squared of theta over 2 equals m over n. So yeah, I have a note there. Some sources have that as the equation. So it really depends on how you would define how many qubits are in the second register, because it depends on your definition, but ultimately the answer would be the same as long as you're consistent. So it estimates theta to m bits of accuracy with success of at least 1 minus epsilon. So the first register contains t is equivalent to m plus the log 2 plus 1/2 epsilon qubits. The second register contains n qubits, or enough to implement the Grover iterations on the augmented search space. So if you wanted to use the alternative method, you can have the second register hold n plus 1 qubits as your definition. So the circuit has these steps. So the first one is initialize both registers to 0. Apply the Hadamard transform as the second step. Then the third step is apply the control G operators 2 to the n times, and then apply the inverse quantum Fourier transform to the first register, and then finally measure it to get theta. And then that's all of it for the quantum part. Once you get the measurement for theta, you can do classical computation to get the final answer. So about the third step, the control G operators, the order of the Grover operators can be reorganized. So without decoherence, the following circuits are equivalent. So this is the ascending order quantum counting circuit. This is how, and this is the descending order quantum counting circuit. You can see how the controlled Grover operators are flipped. If you want, you can just mix and match those Grover iterations, and it would be equivalent. So the measured result, this is how you get the measured result. Theta equals measurement times 2 pi over 2t. So then to get the m number of solutions, you get m equals n times sine squared of theta over 2. So the decoherence. The model of decoherence used is the depolarized state. It's a lot of words here, but then and a lot of qubits here in its classical or how it's implemented in the book. But the gist is there's a chance p to give a qubit either a poly X gate, a poly Y gate, or a poly Z gate. So this is how I implemented it. The reason why I implemented this is for simplicity and its ease to be implemented in Qiskit, because if it's the previous method, for every single possible area or part which could have a depolarizing channel, I would have to add 2 qubits. So that's massive when it comes to some certain quantum algorithms. So for the Deutsch-Josse algorithm, what happened was after each operation, we put the depolarizing channel, and then the value p after every operation, and the value p gets increased from 0 to and increases by 1% every 1,000 tracks for both constant and balanced. For the quantum counting algorithm, we have 2 different kinds. So I used the default example from the Qiskit documentation for this and modified it. So the first experiment was we need to find the boundary by Brian DeHus's method earlier. So skipping through all that math, we have alpha has to be less than 0.00368, which is really tiny. So the expectation is that the circuit would not give the correct answer with even just one single error. So these are the tests I had for that. And these are the measured values and estimated M pairs. The one that's correct is the 4.9. That's the correct answer. So the second experiment is like the Deutsch-Josse experiment. So So the results, analysis, and conclusion. So the three graphs will be shown probability of error versus amount of decoherence. Yeah. Sorry, the formatting's broken here. So the assumptions for Deutsch-Josa is that since we find the answer 0 as constant and everything else is balanced, we can assume that balanced oracles would have less error. For quantum counting, we can assume that it's not going to get the right measurement most of the time. And ascending and descending algorithms with errors on the first register will be similar, and descending algorithm with errors on the second register will be more resistant to decoherence compared to the descending algorithm with errors on the second register. This I got from Hasegawa et al. So here are the results for Deutsch-Josa, thanks to Luigi. He's the one who did this experiment. You'll notice that it's unlabeled. My bad. On the left side, that's the balanced oracle. On the right side, it's the constant oracle, and you can see that the amount of error on the constant grows much higher, while the balanced oracle is not that prone to error comparatively. And then theoretically, using de Husse's method, everything to the left of the red line, the quantum computer will be more efficient than the classical computer. So for the quantum counting algorithm, we have these graphs. You'll notice that the average measurement chance, it's like really bad. You won't get the correct answer most of the time. The correct answer is marked with an asterisk. This is for the first register for the ascending algorithm. Descending algorithm looks like more or less the same thing. But then what's really surprising is that when I tried this for the ascending algorithm, errors on the second register, if there's only one single depolarizing channel, then the computed number of solutions actually was correct for more than half of the time. That was a surprise to me. But then when there were more errors introduced, the chances plummeted as expected. For the descending algorithm, it happened with more of the hypothesis where it wouldn't be as correct. So this is the same these two graphs here, same method. I'm sorry about the lack of labeling, but the one on the left is the ascending algorithm. The one on the right is the descending algorithm. We can see that the curve for the descending algorithm on the right is sharper, so it seems more sensitive to decoherence. But then both of them seem to be very sensitive. So like around 20% decoherence, then it might as well just feel like you're getting a random number. So the analysis is the Deutsch-Josa balanced oracle is resistant to decoherence, while the constant oracle is not. Then for the quantum counting algorithm, the most likely measurement on tests was with one error as expected, but strangely enough, even though those were the more likely measurements, 4.9 was not always the 4.9. The actual answer to that oracle was not the most likely result, except for the ascending second setup. So setups with errors on the first register appear to have more even probabilities. Yeah, and then setups with errors on the second register seem to follow a pattern with more errors. So when it's ascending, it seems like there's a bias for measurements near 1000, and the descending algorithm has more chances at the edges, so 0000 and 1111. So the conclusion is this method is easily done through Qiskit. There's not much coding besides a function that I made, which just adds either a poly x, y, or z gate at around at probability p, compared to trying to implement the depolarizing channel um, in its original method, which is two auxiliary qubits for every single channel, which would take simulating the algorithm forever. It already took a long time for the quantum counting algorithm. So we also see that the superposition and the measured results do not always correspond, as seen with these graphs. And the results follow the study of Hasegawa and Jura. So recommendations, yeah, apply chance-based application. That's what we did for Deutsch-Rosa in the second experiment. And then we can test against other decoherence simulations, test versus different oracles or register sizes, or test on different algorithms. So that's all. Thank you.
Thank you, Pio, for that presentation. The floor is now open for Q&A.
Um,
May I ask a question?
Yeah.
This is Shinya Nishizaki from Tokyo Tech.
Yes.
How different are the simulations in Qiskit from the currently implemented quantum computer? Will it be possible to compare the result obtained with Qiskit with a real quantum computer in the near future or now?
For currently implemented quantum computers, I'm not familiar with how the engineers measure how much decoherence there is for real quantum computers. But for other, if you're also wondering for other theoretical implementations, the one made by Luigi, which was numerical, is another possibility. Another method was wait, I'm scrolling back. Obenland and Desfane had a hello.
Okay.
Hello. My internet cut out shortly. Sorry. Openland and Despain had a method that used that um, that implemented the gates differently. I'm not exactly sure how to describe it, but then their method was different from this one. So there are multiple different ways to test to test decoherence. So will it be possible to compare the results obtained with Qiskit with a real quantum computer in the near future or now? Yeah. It with current again, I'm not sure exactly how the engineers would define decoherence, but we could, as long as we could implement with our simulations.
Okay.
May I add to that?
Yeah,
Pia?
go ahead.
Decoherence is okay. So with regular quantum computers, you can measure things like the result of the algorithm or the evolution of the states of the algorithm. However, when it comes to decoherence, it's a bit harder because decoherence is not something that really comes with the algorithm. It's more of the effect of the realization or how the quantum computer is built. So when it comes to measuring decoherence, at the moment we are not familiar with any ways to actually measure the decoherence in a system in a real quantum computer. But maybe if or rather we were not sure of ways to measure decoherence in a controlled manner But maybe when physical methods for that are when people come up with methods to measure decoherence in that way, then we can compare the theoretical simulations of decoherence with actual measurements of decoherence. But at the moment, because decoherence is a very chaotic thing in general, we don't think that there's a way to measure it in a controlled way. So yeah.
Okay, thank you, Luis and Pio, for answering the questions from Professor Nishizaki. I guess that's our last presenter for this morning. And just to summarize, we have three major categories of papers during this session one. We have quantum algorithms, quantum computation. We have what we call functional reactive programming, and another one for graph databases. I hope for all the attendees, you have learned something new. You are inspired to start your research on these particular topics. And I hope it will start collaborations between different universities. So again, thank you for attending the session one of WCTP. Please be reminded that our afternoon session will start at 1 o'clock this afternoon. So I guess that's it for this morning. So thank you again.